I think today's stuff, and there's a lot in it, and I'm going to try and get it all done. If I don't, I'll do a little video for whatever we miss so that we'll have it covered. Hopefully it won't need that. And we're doing 13.3, and we're going to look at arc length. Actually, there's a bit in the middle. So it's going to be arc length, normal and tangential vectors. We've met normal before, and curvature. So let's start with the first one. Suppose you've got a space curve in 3D space, right? Vector function, if you prefer that time. And you start here at t equals a, and it does its thing. And you finish up here at t equals b. The arc length is the total distance that you traveled. Makes sense? So how do you calculate it? Well, here's the formula. The arc length is the integral from a to b of the square root of this guy derivative squared plus this guy derivative squared plus this guy derivative squared. And that will get us the arc length. This is what the same formula looks like in a much more condensed form. If you find the derivative vector and then you find its magnitude, that's what it's equal to. So that's actually a little bit easier to remember than that, although they are exactly the same. So there are 5 questions where we are being asked to find the arc length. And almost every time you're going to find 3 typical situations. One is the guy inside the square root is a number. So the guy inside the square root is like 17. If you get one of them, you should be really, really happy because they're dead easy. The second kind is that you're going to get the guy inside is a perfect square. So you're going to be finding the square root of something squared, right? When you put them all together and factor them, you get a square. That's very common. And there's some squares that you might not be familiar with, but hopefully you will be by the time we've finished. And the third one is pretty rare, and we might not get one because I haven't looked at every single question, but you will get an expression where you can end up using a u sub. So the algebra is going to be a nice square root of a number, a nice square root of something squared, which basically means that the square root disappears and you're just integrating something that you typically do, or you'd get some really ugly square root, but a u sub might save your life, right? So that's the kind. These are definitely going to happen. I don't know if that one's going to happen. We'll find out. So let's show you the first one. An example of that would be find the arc length of this space curve. And it's 5t, 3 cosine t, 3 sine t. And we're going to be doing it from t is -2 to t equals +2. And negative t's are allowed. Right, so I want the arc length of this space curve starting at t equals -2, finishing at t equals 2. So L is going to be the arc, is going to be the integral from -2 to 2. Here it goes. The derivative of this guy, that's like x of t, is 5. And then you square it. The derivative of this guy, well, if you differentiate 3 cosines, you get -3 sines, and then you square it. And then that's basically your y of t. And then your z of t, just this guy, you differentiate 3 sine, you get 3 cosine t, and you square it. Five squared gets you 25. If you square this, you get +9 sine squared. And if you square this, you get +9 cos squared. Can anybody see a trig identity that would simplify the terms inside the square root?
The 9 sine squared.
Oh, never mind then.
Yeah, sine squared plus cos squared.
Yeah.
So you're saying is it as well, yeah?
I was going
So
to say just group the 9 out to
make the sine plus cosine smoother.
Mm-hmm. So essentially what you get is 9 then, don't you? Because sine squared plus cos squared is 1. 9 sine squares plus 9 cos squares gets you 9. So you end up with 25 plus 9 dt. And that's the integral from -2 to square root of 34 dt. Can you see why a square root of a number is a nice question, right? Easy to integrate. Square root of 34 t. Evaluated at, in this case, -2 to +2. That will get me the square root of 34 times 2. Take away the square root of 34 times -2. Those combine to make it plus, so 2 of them plus 2 of them. Final answer, that the arc length would be 4 root 34. So if you can imagine a space curve representing, say, an aircraft flying in space, and you wanted to know, how far it's traveled in that 4-second period, it would be that unit, right? Arc length, right? The distance along a curve. Now, next one I'm going to show you is one where you get a perfect square, right? So the thing inside the square root is a perfect square, right? It's t plus 1 squared, right? Something like that. This is an example of that would be question 2. And the space curve is made up of various polynomials. And the integral is from 0 to 1. So the arc length is the integral from 0 to 1. Differentiate this guy, and you get 6, and then you square it. This fella, you get 2t, then you square it. This guy, you get 3, that's a third, t squared, and then you square it. Now, the problem with the perfect square ones is that they very often don't look like perfect squares. If I multiply this guy out, you get 1/9 t to the 4, then you get 4t squared, and then you get 36. Now, if you look at that superficially, you would be saying to yourself, no, don't see it. Can't see that being a perfect square of anything, right? So here's a little advice. If there ever is 3 terms inside, right? So if you see it like this, and we'll assume that the question is doable, right? They're not just putting in random stuff that nobody could answer. It will be a perfect square, typically. So I'm going to show you how you figure out what that perfect square is. Write them down in order, biggest power to smallest. Take this guy, the first term, and write down its square root. Right, now if you take that guy, you get a third. What power of t will you get if you take the square root of t to the 4?
That should be a 2.
Great. Don't worry about him, he'll sort himself out. Take the last term, in this case it's a number, but it won't always be a number, and take its square root.
Okay.
Can you trust me? And you do it yourself, I just don't have the time. If you foil that out, I bet you get that guy. Right, you check it out yourself, but trust me, it works. Now, why is that helpful? Nobody in their right mind would want to do a square root in an integral, right? Square roots do not play well with the integral process, unless it's a number, right? Which is the only exception, right? But so you want rid of it. Well, isn't a perfect combination a square inside the square root? Because the net effect is that they cancel each other out. And all you have is that integral. And would you agree that's a Calc 2 integral, which doesn't really involve too much? And since I'm in a hurry, Can you trust me? It ends up being that, because that's what the thing over here says. We're good? So we've seen an arc length question where the thing inside the square root was the number. We have seen an arc length question where the thing inside was a perfect square, right? Perfect squares come in all shapes and sizes, right? I'm trying to see if I can find one. Okay, can't really. So let's look for another perfect square situation. Number 3. Space curve, square root of 2t, e to the t, e to the negative t. And we're going to do it from 0 to 1. Arc length, the integral from 0 to 1, square root of. Okay, if you differentiate the square root of 2t, you get the square root of 2, and then you square it. If you take this guy, you'll get e to the t, and then you square it. If you differentiate this guy, you get negative e to the negative t, and then you square it. You comfortable with those 3 guys? Derivative squared, derivative squared, derivative squared. If you take the square root of 2 and you square it, you get 2. What do you get if you take e to the t and you square it?
E to the 2t.
Correct. And that's negative, but if you square something that's negative, it's positive. And when you square e to the negative t, you get that. Now, there are 3 terms inside that square root. But don't, just because they come out in that particular order, because they come out in all sorts of different orders depending on what you've got, you can't leave them in that way. To do the perfect square thing, you have to put them in biggest to smallest. Well, that's the biggest. Right. Who is next?
The 2.
Does that make sense when I say biggest to smallest? If you want to call that e to the 0, if it helps, right? Now, this guy is a perfect square, even although it doesn't look like a perfect square. It will be, at least in this question. Now, remember what we do. You take the first guy and you find his square root. What is the square root of e to the 2t?
E to the t.
And then you take the last guy and you take its square root. And what's the square root of e to the negative 2t?
E to the negative t.
And can you trust me that that works? You can FOIL it out in your own time. Now, square roots of squares are really nice, because what that leaves you with is that the square root kills off the square, or the square kills off the square root. You are now left with that integral. And would you agree that's pretty straightforward, so I won't do it. So far, so good. I had a quick look at the answers. I couldn't find one that was a U sub, at least none that was obvious. So we're just going to show you 2 situations. And number 4 then is an algebra situation, and number 5 is, what do you do if nothing works? You know, because some integrals just don't simplify, right? They don't come out nice. What do you do? And we'll talk about that when we come to the last one. So in this one, we have cosine of 3t plus, well, not a plus, comma, the sine of 3t, comma, 3, the natural log of cosine t. Well, that's a bit weird. And t is going to go from 0 to pi upon 4. So the arc length is going to be the integral from 0 to pi upon 4. If you differentiate the cosine of 3t, you do get negative the sine of 3t. But it is a chain rule, isn't it? So you also get a times 3. Are you comfortable that the derivative of that is negative 3 sine 3t? You comfortable where that extra 3 came from? Right. Same kind of thing happening with the next guy, but this time it's 3 cosine 3t. And you square it. And then this horrible guy. 3 times the natural log of cosine t. Any suggestions?
The derivative of what's the derivative of the natural log again?
Okay, what is the derivative of natural log? Help them out.
It's
One
1x or something like that?
over the variable of something, or one over.
Okay, so 3 natural logs is going to be 3 over cosine t. Don't you have to times by something?
Yes, that is the chain rule, which make it become a negative cosine. Well,
The derivative of it.
Sine.
So negative sine. So I'll show you that on its own. If you want to differentiate 3 natural log of cosine t, think of that as your inside function. So you get 3 over the thing times the derivative of the thing. So what you're looking at is negative 3 sine t over cosine t. Can you see anything that would simplify to?
Yeah,
Oh,
3
by the way,
tangent.
and forgot to square it. Negative 3 tangents, agreed? Right, and I want to square it. So that will get me plus 9 tangent squared. Okay, so if you square this fella, you'll get 9 sine squared of 3t. If you square the middle one, you'll get 9 cosine squared of 3t. If you differentiate this guy, you end up with 9 tan squared t, right? Can you see anything you could do to these two guys?
Turn it into 9. Oh, the 3.
Yeah,
What happens
no,
with 3 inside?
it doesn't matter, still 9.
Okay.
As long as it's the same guy, right? Sine squared t, sine squared 2t, sine squared 20t, as long as the other one matches it, it's just the same as sine squared plus cos squared, right? So that's just 9. And then we have 9 tan squared. And I'm going to do the next part. I'm pulling out 9. And now I'm leaving that left.
Is there an identity for that?
Yep, there is. Do you know what it is?
Secant or something like that?
Very close. Secant.
I would actually pull the 9 as a 1 plus tangent square out.
But what is the 1 plus tangent squared equal to? That's what we're puzzling over right now. And you were darn close, Jeremy. You weren't a mile away when you said
Is it
secant.
secant squared?
It is. It's secant squared.
Oh, I just said secant.
Yeah, that's all you were short of.
All right.
Pretty much done most of it. So square root of, well, I guess it's perfect square. 3 secant t dt. So far, so good. Then all we need to do is find the integral of secant t, which I doubt very much if anyone, including me, has bothered to memorize. But you can go and find it. And if you find it, I'm just looking at what they tell me it is. It's 3 times the natural log of secant t plus tan t. And they put a little absolute value around it in case it's negative, because logs don't like negative things. So that is going to be the integral of 3 secant t. you evaluate it at 0 and at pi upon 4, and you cannot do calculators because they want exact values, right? So secant to pi upon 4, for instance, is √2. Tan of pi upon 4 is 1. So that's going to be 3 natural log of, what did I say? 2, yeah, 2 plus √2 plus 1. Oh, good, I was right. Now, what do you do if you get an arc length question and they say this at the end? Use a calculator to whatever, 3 decimal places. The minute you see that, you don't need to worry about anything pretty happening. You just need to get to a point where you can let your calculator evaluate it. So I'm going to show you that by just making up one. Won't even be like question 5, but it doesn't need to be. So I'm going to do sine t e to the t squared, right? Would you agree that is highly unlikely to come out pretty? And we want to do the integral, say, from, I don't know, 0 to 1, right? Nothing weird happening, I don't think so. So the arc length will be the integral from 0 to 1, the square root of this guy's derivative, which is cosine t squared, this guy's derivative, which is e to the t squared, and this guy's derivative, which is 2t squared. And so you'll get the integral from 0 to 1 of cos squared t plus e to the 2t plus 4t squared. Now, it won't take you long to look at that and say, it's definitely not a perfect square, and there's not a U sub in the world that would ever get you out of trouble. But since they told us to use the calculator, I wouldn't even worry about needing to know that. But I do want to know how to get the answer on my calculator. So here goes. Y equals, clear it out. Type in this function here. See this guy here? So it's going to be the square root. Instead, to do cos squared, it's a bit messy. You need a bracket, cosine x instead of t, right? Close that bracket and squared. So basically you do cosine of x in brackets whole squared, right? Now you want e to the 2t, which is a lot easier, plus e to the power of 2x instead of 2t. And then you want plus 4x squared and close off your bracket. So essentially type that guy into your calculator. So far, so good? Now, go to your window, start at 0 and finish at 1, because start at 0, finish at 1. Then you go to this button here. See this button, second from the right, the blue one? So second calc. And right down at the bottom, they have the integral symbol, and that's where you can get your answer. So I'm going to hit enter. And I just made a mistake. Come on. Good. Oh, I didn't make a mistake. I thought it was in degrees. I thought, oh, that's why it's taking so long. It's just taking so long because it's a really old calculator. So here we go. Lower limit 0, press enter. Upper limit 1, press enter. And the answer is 2.2157 and whatever you were looking for. So if it was to 2 decimal places, 2.21. That isn't a horizontal line, by the way, but I don't know what it is, but I don't care because we only want the number, don't we? If you wanted to see what the graph looked like, zoom 0 is zoom to fit. And this is what it looks like. I think my body is just, no, okay, it's good. Then I'll do second calc, number 7, lower limit 0, upper limit 1. And then for those people who actually want to see the thing doing it properly, can you see it filling up the curve? And my battery's died, so can you trust me that was right before it did die? And that is the end of ArcLand. Any questions before we move on to our next topic? Are we good? Okay. So there's 3 topics for today. This paper in the way there. The second topic is here at the top. We've actually done half of it before. Remember, we calculated what was called the unit tangent vector. And to do the unit tangent vector, you found the derivative, and then you made it a unit vector by essentially dividing by its magnitude. Well, there's a second special vector called the unit normal vector. And what you do is you take this answer and you differentiate it. And you make this answer a unit vector by dividing by its magnitude. And if you're interested, which you may or may not be, I'll actually try and explain what these guys are telling us about the motion of an object. So I'm doing my roller coaster curve, R of t. If you choose just a point there, isn't the unit tangent vector that guy? It's basically, that's the direction. They just make it 1 unit long. So the unit tangent vector is the vector you shoot off to your death. Now, there are 2 other major forces involved in an object moving in 3-dimensional space. There is that guy there. That's what your unit normal looks like. If you've ever been in a roller coaster and it goes round a sharp bend, have you noticed that there's a force pushing you to the side? And the direction of that force that's pushing you to the side is what the normal vector is doing. Now we're going to calculate that one and that one, but for completeness, I want to tell you the third one. In my case, it looks like it's vertically upwards because it is. The third and final one is called the unit binormal vector. And these 3 vectors have one very interesting property. They're all orthogonal to each other. Now that third vector is, if you've ever been in a roller coaster, isn't there sometimes the way it moves, don't you get lifted out of your seat or pushed into your seat? The unit binormal is that force, right? It's throwing me up or it's pushing me down. So can you imagine if you're interested in the movement of an object, wouldn't these 3 vectors tell you quite a lot about what's happening at any given point, right? Okay. I believe what they do is, do you know those aircraft that you can go up and they simulate weightlessness? Now, the way they simulate weightlessness is that they do a helix. So they don't just zoom down the way and, you know, because if you did that, you just get pushed into the back of your seat, right? That wouldn't feel weightless at all. And they're no good shooting vertical upwards because that does the same thing, right? You're not going to get into that. But what they do is they design a big loop, a big helix, and they spiral it down it. But it's designed in such a way, and they go at certain speed, that there is a positive upward motion. In other words, you will be lifted out of your seat. Maybe not perfect weightlessness, but that's how they make it happen. Cool? So, the less cool for some of you is calculating it. It's not hard to do. It's just ugly to do. Unless you're really lucky and they give you a very simple example of it. You're never going to get very nice, what's the word? Very nice results out of it. But nevertheless, here's an example. Here is my space curve. 3t squared sine t, take away t cosine t, and cosine t plus t sine t. We're being asked to find the unit tangent and the unit normal. So let's show you how that works. The unit tangent is 1 over the magnitude of this guy. Oops, that's an R. The derivative. Okay, so I'm going to have to find R dashed. Differentiate that guy, you get 6t. Differentiate this guy, you get cosine t. And this fella, you're going to have to do a little product rule. So trust me, negative cosine t minus minus gets you a plus 1 times sine t. So you get that. And then you do this one and you get negative sine t. And then you differentiate this guy with the product rule and you get 1 times sine t plus t cosine t. F dash dash, there's a t there, right? So the derivative function is 6t. They get cancelled and you have t sine t. And they get cancelled and you have t cosine t. Okay. Not too bad, could have been a lot worse. Now I need to find the magnitude of it. 6t, then you square it. Now notice I'm not differentiating in here, it's really just the components, right? Not doing anything to them except squaring them. In case you get into the habit of squaring the derivative. You only square the derivative when it's an arc length, right? When it's just a normal magnitude, you just square the thing as is, right? You don't do anything to it. Now this guy is 36t squared. This guy is t squared sine squared t, and this guy is t squared cosine squared t. Are we comfortable with it so far? Now, style points is really indispensable here. You've got to do the best you can. We've done a lot of cos squares and sine squares today. What do they two things add up to?
T squared, if we just ignore the sine squared plus cosine squared equal 1.
Yeah. And then since they're all times that, can't you, oops, that's, can't you now do that guy? And that can be a little bit ugly, but quite a nice finish. Are we good so far? Now you put the magnitude guy, which is the one we've just found, and you put it along with the original, we will now have the unit tangent vector. The unit tangent vector then is going to be 1 over that guy, right? The magnitude, with the derivative vector, 6t, t sine t, t cosine t. So the unit tangent vector is 1 over the magnitude of the derivative times the derivative vector, right? 1 over the magnitude, derivative vector. Now you put them all together. The t's cancel. The t's cancel. And the t's cancel. So we have the unit tangent vector, which we could have done on Monday, right? Same idea. Well, what's the new guy in town? The new guy in town is the unit normal vector. So it's a bit like pretending that's your starting point and doing what we just did all over again, right? So I'm going to find the derivative of the unit tangent vector. Well, differentiate a number, you get 0. This is basically a fraction version of sine, so you get cosine t over the square root of 37. And this guy is negative sine t over the square root of 37. Are you comfortable about the derivative? The 37 is just a number. Now the magnitude of this vector is the square root of 0 squared plus the cosine of t over the square root of 37 squared plus negative the sine of t over the square root of 37 squared. So the magnitude of this vector is 0 plus cos squared over 37 plus a sine squared over 37. Do you see the square roots when you square them are no longer square roots? Style points. What does that become?
1 over 37 in a square root.
Agreed? Which I'm now going to call the square root of 1 over the square root of 37, which I'm now going to call 1 over the square root of 37. You comfortable with that? Now you put those pieces together and you will now have the unit normal vector. The unit normal vector is 1 over the magnitude of that guy times that guy. So it's going to be 1 over that weird fraction, and t dashed is 0 cosine of t over the square root of 37 negative the sine of t over the square root of 37. Isn't 1 over something just the square root of that? It's essentially the reciprocal of a reciprocal, right? Like 1 over a half gets you 2 times this guy. Multiply through, 0 times something is still 0. Those come out nice as a cosine, and those two come out nice as a sine. And that is the unit normal vector. And you'll have to trust me, but if you take the unit tangent and the unit normal, they are orthogonal. And if you don't believe me, just do a dot product and I bet you'll get 0. Are we good? Now, they've tied together with this another thing called curvature. So they're kind of blending two different ideas together. Curvature. And we use that letter, it looks like a K, but it's actually the Greek letter kappa. So you will say kappa of T when you say it. So let's talk about what you're calculating when you get the curvature, right? When you find kappa of T. So let's imagine that we're doing a roller coaster thing. And it does its whatever, right? That's R of T. And we're interested in some arbitrary guy that we're going to call T, right? So if T equals 5, that's where T equals 5 is, right? At every single point on the curve, there is a thing called its curvature. And curvature is measured in terms of circles. So I'll give you an idea. If you had a very small circle and a very big circle, intuitively, aren't you going round quicker with a little circle than with a big circle? And so little circles have kappa that could be things like 100, right? And little circles have kappas like 3. Now, how do you measure the curvature of a circle? Kappa is 1 over its radius. So you imagine if you've got a very small radius, won't 1 over it be a very big kappa? Whereas if you've got a very big radius, won't 1 over it be quite a small value, right? So all space curves are compared to the circle that would have the same curvature as. So imagine, before we imagine that, let's look at the 2 extremes. The least curved movement in the world is a straight line. Agreed? According to the definition that we've given, what will the curvature of a straight line be at any of its points?
0.
It would be 0. Technically, wouldn't you need a circle of infinite radius to generate a straight line on its edges, right? Now, there's one other extreme, because kappa can never be negative. What would the curvature of a point what would it look like if its curvature kappa was infinite? What's the most curved thing in the universe, do you think? And it's not, I don't know if it's intuitive or not. When I tell you,
Is that a tornado?
Well, that may be in real life. That's a pretty bad curvature, but that just means it's moving fast rather than the curvature itself. Right. Any idea what the shape? No, I'm totally good answers. Just a dot. A single point in space has infinite curvature. Yeah, at the extremes, things get a little bit weird, right? Okay, so a black hole would have infinite curvature probably, right? Anything that gets close to a black hole is going to have a hard time. So I've given you the background of what it is that you calculate. So let me tell you the formula for doing it. The curvature at t, kappa of t, is the magnitude of that guy divided by the magnitude of this guy. Well, since you've already had to find these things in the earlier questions, it's not so much extra work, isn't it? Just finding the guys that you've already found and putting them in the right place. So the magnitude of this guy was 1 over the square root of 37. Right? Magnitude, make it positive, I guess, but you already know that. And the r dashed guy, what was the magnitude of the r dash guy? Hold on, put it somewhere where I can't find it. And the magnitude of the r dash guy was the square root of 37t. So I'm just going to make this a little bit prettier by bringing that downstairs. There's your curvature, 1 over 37t. As t gets bigger, won't the curvature become closer and closer to 0? So I can tell you that this space curve, as much twirling and spiraling as it does, as time goes on, won't it just basically find a direction and just go straight? 0 curvature, right? Straight. And that is how you get curvature. Now, there is a lot of work involved, as you can imagine, doing just one of those guys. That was question 6 I've done. 7, 8, and 9 kind of do the same stuff. I'm just scanning through them. I don't know which one I want to do. It's a time issue, really. Whichever one I do, it's going to be horrible. So why don't I try 8? And in question 8, the space curve is t squared and 4. And we are going to find unit tangent, unit normal, and curvature, right? That's the 3 things we're going to do. So I will find its derivative, which is 1, 2t, and 0. I will find the magnitude of that derivative vector, which is the square root of 1 squared plus 2t squared plus 0 squared. And it's 4t squared plus 1. And no, that is not 2t plus 1. I wish it was 2t plus 1, but it isn't. You can't simplify it, right? There's really nothing. You just got to live with it. Which means that the unit tangent vector is going to be 1 over that guy with this derivative. So I'm now going to put them together with a 1 over the square root of 4t squared plus 1, 2t over the square root of 4t squared plus 1, and a 0. It's the only decent piece of the answer. Are you comfortable about the unit tangent? To save time, can you imagine I differentiated that guy? And trust me, can you imagine how much work that's going to involve? Done. Find the magnitude, which is even going to be uglier. And then you put it all together. And here is one that I prepared earlier. You will get the answer, negative 2t over the square root of 4t squared plus 1. 1 over the square root of 4t squared plus 1, comma 0. So you might be surprised that it actually isn't as ugly as it might seem. And then you get the curvature. And that is going to be the magnitude of that guy divided by the magnitude of that vector. Right, now, I don't have that guy handy, so can you just trust me that you end up with that guy when you're finished? So you're going to have to differentiate this guy, obviously, and find its magnitude. Stick that answer on the top. You're going to take r dashed of t, which I actually do know, right? It's that guy there. And then tidy it up, and evidently they tidy up quite nicely, and this is what you get. So, I wish I could have done more, but it's mostly time consuming, right? It's just ugly and long, not necessarily difficult per se, but it is horrible. Which gets me to our last chunk of questions.
Could I see that piece of paper again?
Sure. There is another way to calculate the curvature formula. This one uses the magnitude of the unit tangent divided by the magnitude of the first derivative. This one uses that formula. So that's the kind of thing you want to have in all your little cheat cards, right? Various formulas of various things. So these questions deal with finding only the curvature by calculating this. Me personally, I prefer this way than that way, right? That's just me. But if you're already finding the unit tangent and the unit normal, would you agree this would be sensible, right? But if the question was only find curvature, I think this, as long as it is less. Well, for me, it is less work. Can't talk for everyone. Oh, was that enough time for you? Sorry. Okay. So 10, 11, 12, and then there's a little guy at the end. So here we go. Which one shall I pick? Pick question 11. And R of t is equal to the square root of 6t squared, a 2t, and a 2t cubed. Yeah. A lot of these questions use the IJK notation. I always write things like that, no matter what the question started life off as. So I need to find the first derivative and the second derivative and then do some stuff with it. So I'm going to just find the derivatives first. The first derivative, multiply by the power and reduce the power by 1. First derivative, first derivative. Are we comfortable with that? Second derivative is just differentiate that guy. 2 root 6, 0, and 12t. Again, you comfortable with that? This is a bit messy. This isn't anywhere near as messy. I need to find the cross product of these two guys. So that's where I'm going next. The cross product of these two vectors, because they are vectors. So we're used to doing vectors with numbers, but you can do vectors with variables like t as well. The second row is this guy. 2 root 6t, 2, 6t squared. The second row, the third row, I guess, is this one. And then we do so many i's, take away so many j's, plus so many k's, right? That's how you get all of these guys. Here it goes. Cover up. Right? The I column. Major diagonal 24t, take away nothing. 24t. Middle one. Major diagonal is 24 root 6 t squared. Take away 12 root 6 t squared. Okay, last one. 0, take away that guy, which is what? 0, take away 4 root 6. So this guy is 24t. That guy and that guy are the same guy, so you get positive 12, then you take it away. And that guy is negative 4 root 6. Are we good so far? Right? I, J, K. This fella, this fella, this fella. Now you find its magnitude. The magnitude of any vector, including this one, is just that guy squared plus that guy squared plus that guy squared. Still okay? If you take 24 squared, I don't know if I've got any just left in this thing, but I'll try it. 24 times 24, 576 t squareds. That's basically 144 times 6, which is 864 t to the 4s. And that guy is 16 times 6, which is 96. Write it up here. Style points. Anything you think you might be able to do here?
You square it out.
Say again?
You get a square from it.
You will eventually, but I wouldn't try and do it right now.
Okay.
But you're right, you are going to get a perfect square out of it. Just look at these numbers. I don't want to deal with numbers this big, right? Just don't want to. So is there anything you might be able to pull out as a common factor?
Why don't we just pull out a 4?
Yeah, well, could work. You can do better. So we're doing a bidding competition. Viet has bid 4. I'm saying
24.
I'm not taking 4. What you raise me? Give me another number that also works.
96.
96.
96. Whoever said it got the prize. You get it first. Can you imagine? There's probably a clue in here just because of numbers, right? So I'll pull out 96, and then I'm going to have to do some calculations here. And while I'm at it, I'm going to put it in order. So that one goes first. So 864 divided by 96, I get 9 t to the 4th. I'm now doing the 576 divided by 96, and that gets me 6 t squared plus 1. Right, Jeremy, I'm going to pull out that 96. Right, get out of the road. And just focus on this guy. He is going to be, yes, a perfect square.
3t squared plus 1.
Once you've seen a few of them, isn't it kind of easy to pull out the perfect square? 3t squared and a 1. This guy here is 6 root something, 36 times, help me here, is it 36? No, it's not 36, it's 16. So how about 16? That's 4 times 6. Okay, we got it. And this guy gets you 3t squared plus 1. And we have got one piece of the puzzle. And as bad as that is, you try getting a unit tangent and a unit normal out of that, and you'll just be in as much trouble, if not more. Now, the other guy isn't too bad. The other piece of the formula is just that guy cubed. Right, so I'm going to find that fella and then cube it. Well, the first derivative is this guy here. So its magnitude is 2 square root 6t squared plus 2 squared plus 6t squared. And that guy's going to get you 4 and 6. That's going to get me 24t squareds. That guy's going to get me 4. And this guy's going to get me 36t to the 4. Any suggestions what I might do to this expression to get a better answer, a nicer style point answer?
You might want to pull out a 4.
I think you would. Would you also suggest I put them in order of biggest power to smallest? So when I do that, I get 9t to the 4, I get 6t squared, and I get plus 1. And I'll pull out the square root of 4, which gets me 2. And what does that guy look like as a perfect square?
3t squared plus 1.
You agree? Every time you see it, it gets a little bit easier the next time you see it. Which means that this fella comes out, essentially, as that guy. Of course, we want this guy cubed. So cube that guy, you get 8, and cube that guy, you get that. Comfortable about cubing that answer? Right. So all I need to do now to get the curvature is take the first answer and divide it by this one. So the curvature at t is equal to, I've lost the guy.
The first variable is on
Oh, here it
top of
is.
the paper.
Yeah. Yeah, so that was the cross product, right? That guy there, and over this guy cubed, which is, and again style points. Any suggestions what we might do to make it pray?
4 and 8 just, well, they cancel out, which lead to on bottom, and then let's see. So the top and bottom also have the pre-t square plus 1 in common. So we just take one of it out. Left down is 2 variable of it.
Comfortable? Jules agree it's a lot.
Got the squared.
Did I do a square? Oh, I forgot my square. Well done. Because I only used up 1, not 2. Are we good? Now, since I've got this in front of me, and I have no real idea what the original shape looked like, which was this guy here, I can tell you some things about this particular curve. And that is, it's never, ever quite a straight line. Although, as t gets larger and larger, doesn't it become closer to being a straight line? And if you wanted to know where it was the most curved, right? In other words, in all its journey, where would you get the largest curvature? I can look at that and tell you right now that the answer is √6/9. How do I know that? No, √6/2. I apologize. Isn't the smallest this is ever going to be is when t is 0. And when t is 0, that's 1. So √6/2 times 1 squared, which is no mistake. So I know that this shape starts off at its most curved, and then as time goes on, it gets more and more straight. Whatever, you know, whatever time it takes to do that. Are you still with me, guys? Right. Okay. Now, got time for that one. Right. I'm going to do the last question first. That way I'll know if I have time for the one that comes after this. The final question is a little bit different. There is a formula which you've never used because it wasn't a thing we'd expect you to know about for 2D functions. You can find the curvature of a 2-dimensional function, right? Just a normal calc 1 function, right? 2-dimensional function. And the formula for it, well, first it's called kappa, of course, x, which is the x coordinate. And it is equal to the second derivative. Now, that doesn't so much mean magnitude. That just means the absolute value, right? So it makes it positive. Divided by 1 plus the first derivative squared, all raised to the power of 3/2. Now, I'm not a sciencey person. I'm not sure why you would want to know the curvature of a 2-dimensional object, but if you did, here is the horrible formula for doing it. So let's give you a function and calculate. Let's calculate its curvature. So I'm going to do a pretty boring curve because I want it to be relatively easy to do, which is that guy. Based on just that shape, would you agree that it's going to be most curved at x equals 0? And less curved the further away from 0 you get. So I wonder if that comes up in the calculation. Well, all you do is you find the first derivative and you find the second derivative. And then you plug them in here. And so curvature is the second derivative. Now, if that had been -6, right, because it could have been. If that had been -6, you just make that 6, right? That's what that's about. Okay, so if the second derivative was a -5x or something, right, that kind of thing, but mostly numbers. Now, on the bottom, it's going to be 1 plus the derivative, which is 6x squared raised to the power of 3/2. So that's going to be 6 over 1 plus 36x squared to the power of 3/2. And I can tell you that it's going to be its biggest value when x is 0, which we predicted. And in fact, if I told you x is 0, wouldn't the curvature be 6? And just to remind you what the curvature of 6 means, it means the radius is 1/6. So if you tried to do a circle that fitted in here, that had the same curve as x squared, or 3x squared have, that circle would be the radius of 1/6. Right, you imagine that's a pretty small circle, right? So it's curving quite quickly. So curvature is 1 over the radius of the circle that has the same. So if you want to visualize it, 1 over that number is how big the radius is. Big curvature, small circle, right? That makes sense, because small circles curve faster than big ones. Are we good? Right, so I do have time to do, and we did cover it all, let's go figure. One last question, so here we go. Question 12. We are going to find the curvature of this guy. It's pretty ugly, but not just the general curvature, right? The one with T's. We're going to find the curvature at one specific point on the curve, right? So if you imagine you've got the curve in at 3, 0, 0, right? That's the only place I want the curvature of. I need to know what T that is equal to. What is the value of T in here that would generate 3, 0, 0?
1.
1.
Y'all agree? Okay, so that's the guy I like. Don't care about him anymore. Don't need him. First derivative, 6t, 1 over t. If you differentiate this, you're going to have to do a product rule. So that's going to be natural log of t plus 1. You just have to check later why that's the case. Second derivative at t, 6, negative 1 over t squared, 1 over t. Right, if you differentiate 1 over t, you get negative 1 over t squared. If you differentiate a log, you get 1 over t. Cross product coming up. I have an I, a J, and a K. A 6t, a 1 over t, and a log of t plus 1. I'm going to have a 6, a negative 1 over t squared, and a 1 over t. And I'm probably going to need all the room I can get. So cover that guy up, cover that guy up. You multiply the major, you get 1 over t squared. You multiply this, and you get minus the natural log of t, well, plus 1 over 8 of t squared. So I guess that's going to be a plus when I'm finished. And that's the i's. Takeaway. Let's do the j's now. That guy times that guy is 6. Take away those two guys. And that's the J's. Move over to that one. This guy times this guy is negative 6 over t. Take away this guy times this guy, so take away 6 over t. And that's the k. Okay, what's this going to get me? 1 over t squared plus log over t squared plus 1 over t squared. So I'm going to get 2 over t squared plus log t over t squared. Yeah. 6 take away 6. Oh, the 6's cancel. And minus 6 log t, make a negative of it, you get plus 6 log t. This guy take away this guy gets you negative 12 over t. And there is our guy. And I just made my life 10 times harder than it needed to be. I'm only interested in the answer at t equals 1. I should have done this. R dashed of 1 is 6, 1. The log of 1 is 0, 1. The second derivative at 1 would be 6, negative 1, 1. Would you agree getting that cross product would be a lot less work than that horrible mess? But it's the end of the night and I'm getting tired. You only can do that, of course, if it's saying find it at one specific number. If they just wanted the general formula, I would have to have fought my way through. The reason why it came to me was, do you know I have to find the magnitude of that? And I was thinking, oh God, I don't want to find the magnitude of that. Surely it can't be. And then I went, let's use them. So the cross product with only the numbers. I, j, k. 6, 1, 1. 6, negative 1, 1. Little cover up thing, right, whatever, that guy. Oops. I don't need that, right? 1 take away negative 1 is 2. Middle guy, 6 take away 6 is nothing. Negative 6 take away 6 is negative 12. So unless I screwed up somewhere in the signs, pretty nice vector. Right, now get its magnitude.
Funny enough that if you actually plug 1 into that formula, then you did actually get the
same answer.
Yeah.
Which is a good check that I've actually done this correctly, right? So it did work for that. So 2 squared plus nothing squared plus negative 12 squared. That's 144 plus another 4. So that's the square root of 148. I can handle that. I'll circle around it to remind myself. Now I'm going to find the magnitude of the first derivative, which is this guy. So it's going to be the square root of 6 squared plus 1 squared plus 1 squared, which is the square root of 38. So I can now find the curvature at t equals 1. It's the magnitude of the first and second derivatives cross product divided by the magnitude of that guy cubed. Oh, so I forgot to cube that guy. So it's going to be the square root of 148 all over the square root of 38 cubed. Wow, okay. I don't want to leave that answer, I really can't. I should try my best, right? Shouldn't I, to at least make it sort of a kind of a pretty, right? I can't see too much to do with that cube except to call it 38, the square root of 38. Are you okay with a square root cube to get you a whole number and the square root bit left over? All over that guy. Right, I'm scanning through my brain, anything with 38, 2, well, 2 doesn't matter, 4, no, 16, no, 9, no, forget it. How about 148 then?
4.
4.
So 2. So get
What
it
do you
2
get?
outside. 2
Which one?
on the top.
So what does that come out as? 4 times?
Uh,
Okay, let's do 4.
5.
That's 30, 28, 7,
37.
right?
37.
It's 37. Okay, so we're going to get 2 root 37 over 38 root 38. It's going to get me 19. Okay. Comes a point in time where you just have to take your losses, which you could have probably not much more I could do to that. Could I rationalize the denominator? Sure. Wouldn't the answer probably look even uglier than it is right now? So there's probably no point.